In Chapter 7, we talk about proving different types of statements. So far, we focus mostly on proving conditional statements of the form P implies Q. So now we're going to talk about proving biconditionals and then equivalent statements. So they're very similar to what we've already done. So let's just talk about 7.1 first, which is on biconditionals, or statements of the form if and only if. So remember, right, if we have P if and only if Q, that's really the same as saying P implies Q and Q implies P. So if I want to prove an if and only if statement, really what I'm going to do is I'm going to first say, I like to use my little arrows to kind of help lead the proof. So I'll put that kind of in the margin to lead kind of as we're working. So then I'll prove the first part, P implies Q, that conditional. And then when I'm done, I'll do the other part. I'll prove that Q implies P. Right, so really I'm just going to go through and do two separate proofs. And then each of these we can do either a contradiction, a contrapositive, or a direct. So I'm sort of going from least likely to most likely here. And often what we'll see is one way is going to be helpful to do direct. And because of that, that means one side is easier to assume. So we're probably going to want to do a contrapositive for the other direction, so we can end up just assuming something that's pretty similar form. So let's go ahead and look at an example of that. The example we have is we want to prove that x is even if and only if 3x plus 9 is odd. So just to kind of add some symbols here, right? I've got my P and I've got my Q. And so first I'm going to show this implication, my P implies Q. I notice that one of my statements is just about x being even, where the other one is about this more complicated expression, 3x plus 9 being odd. So I'm probably going to want to assume the one about P. So if I'm going in this direction, P implies Q, I can assume P by just doing a direct proof. So I'm going to assume x is even, that's my P. So x is equal to 2m, where m is in z. Now I want to try to show that 3x plus 9 is odd. So we'll start with that 3x plus 9 expression and say what I know for sure it's equal to. X is equal to 2m, so I get 3 times 2m plus 9. I know I want this to be odd, so it should be 2 times something plus 1. So I'm going to write that as 6m. And I'm going to pull off a plus 1 from this so that I'm ready to go to put it in that odd form. I notice my first two terms have a factor of 2. So I get 2 times 3m plus 4 plus 1, where 3m plus 4 is an integer. Thus, that 3x plus 9 is odd, which is what we wanted to show. Now, if I want to go backwards, again, just in my handwriting, I'm just going to write this little backwards arrow to indicate that I'm going to show the opposite direction. Remember, that opposite direction is called the converse. So you can always include something like conversely in your proof to indicate that we're going to do the converse next. All right, so conversely, now I want to try to prove my Q implies P. So either I can assume 3x plus 9 is odd, or I can assume the negation of the P now, that x is even. The negation of that x is even, which is that x is odd. So I think it's going to be easier to do a contrapositive for my converse. So I'll put in the contrapositive as well, by contrapositive. Assume not P, because that's the negation of the consequence in this example. So x is odd. So x is 2. I used m up here, but it was in a completely different proof, so I can reuse that if I want, but I'm just going to go ahead and pick a new letter, 2n plus 1, where n is in z. Same thing, 3x plus 9 is 3 times 2n plus 1 plus 9, which is 6n plus 3 plus 9. Here I'm trying to show that this is even, so I want to be able to pull out that 2. 3n plus 6, where that 3n plus 6 is an integer. Thus, we get that 3x plus 9 is even, which is what we wanted to show, because I was doing the contrapositive of my converse, not P implies not Q. Right, so really what I did here, instead of proving P implies Q and Q implies P, I did the equivalent thing to showing, which was showing that P implies Q and not P implies not Q. So it's helpful to remember that because not P implies not Q is logically equivalent to Q implies P, because it's that contrapositive of that converse, that is also something that you can do in these if and only if proofs. And often that's going to be helpful for us. All right, so we've got a discussion question for you. So I want you to see if you can prove that A plus B is odd if and only if A squared plus B squared is odd. So go ahead, try some different approaches on that, see if you can prove one side or the other of that if and only if, or if you can get both of them. This is shorthand here. I with 2 F's is my shorthand for if and only if. So when I'm feeling lazy, I will write it like that. All right, I wanted to talk about section 7.2 in the same video because they're both pretty short. So section 7.2 is about proofs of equivalent statements. So I'll kind of pop that in up here, equivalent statements. And the way that we often see this used is in the form of this, the following are equivalent. So what do I mean by the following are equivalent? So this TFAE stands for the following are equivalent. It means you're going to list a bunch of statements, and they're not all necessarily true, but they're all equivalent to each other. So as soon as one of them is true, then all of them is true. And as soon as one of them is false, then all of them are false. Let me just spell equivalent correctly here. So that just means they're either all true or all false. And as soon as you know, one is true or false, make that a little more readable there. As soon as you know that one is true or false, the rest are too. So the rest are true if one is true, and the rest are false if one is false. So I've got a screenshot in here of an example. It's called the invertible matrix theorem. And you might have seen this in linear algebra. And this is sort of, I think, a really famous equivalent proof, because there's just so many statements that are equivalent to each other. So it says, a matrix A is invertible. So I'm just going to call that statement A, if and only if any, and hence all, of the following hold. Right, so really, I have all of these different statements, and it's saying that A is true if and only if B is true. But A is also true if and only if C is true. So that means that if C is true, well then B is true. Or so if C is true, then A is true, then B is true. So C implies B. But also, if B is true, then A is true, then C is true. So B implies C as well. So again, as soon as we get one of these statements being true, then we get all of them being true. So what we want to ask ourselves here is, how would we go about proving a statement of this form? So let's look at that in the next slide. So the way that we should think about these, right, I'm using sort of some shorthand here. I've got the theorem is the following are equivalent, and then I'm just listing a bunch of different statements, A, B, C, D, E. And the way that we should think about this is it's saying A, if and only if B, if and only if C, if and only if D, if and only if E. So if I tried to show that directly, I could show, right, those two proofs here, and then these two proofs here, and these two here, and these two here. So that's one way of showing it. But I can also do sort of some sneakier things, right? So maybe I show A implies B. I show B implies C. I show C implies D. I show D implies E. And then I show E implies A. So I'm just going to move my C over a little bit. Right? Now this is just 1, 2, 3, 4, 5 proofs. And let's see if we're able to show, given any statement and any other one, that we can get from A to D, for example. Right, so from any of these statements, I should be able to imply the other one. So if I start at A, if A is true, B has to be true, which means C has to be true, which means D has to be true. So I do know that A implies D. Do I know that D implies A, for example? Well, if D is true, then E is true, and if E is true, then A is true. So I do know that D implies A. So really my proof is just going to be any cycle, so any collection of arrows that creates a path from any statement to any other statement. Right, so I could say, okay, from A, maybe I say, oh, A implies C, C maybe implies D, and D implies A. But then A also implies B. So let's say I've proved all of this, and I ask myself, can I get from C to B? Well, C gives me D, D gives me A gives me B. So that's good. But then going back, can I get from B to C? Well, from B, I can't go anywhere. So let's change that to an if and only if. So now B goes to A, and then A can go to C. So I can get to C, I can get to D. All right, so I can get from B to anywhere. I can get from anywhere to A, and I can get from A to B. So this is also another proof thing. This one, let's see, requires 1, 2, 3, 4, 5 proofs also. That would also allow me to prove that the following are equivalent. So we're just trying to look for these chains of equivalencies, or these chains of implications, that are allowing us to get from any statement to any other statement. All right, so my exercise for you for this section is to think about all of the different ways to prove the statement, the following are equivalent. We've got A and B and C, without any extraneous proofs. So what do I mean by an extraneous proof? Let's say I prove A if and only if B, and then B implies C, and C implies A. Right, so let's think about this if and only if here as two different arrows. If there's any of these arrows that I can delete and I still have a valid proof, then that means that that proof was extraneous. So I notice that this arrow here, I can get rid of it, and I would still have a valid way to get from any statement to any other statement. So that guy is an extraneous proof. So I want you to see if you can come up with all of the different ways to draw this out where you don't have any of those extraneous proofs. It's a good challenge exercise. But like just like a challenging exercise, not no one necessarily that's going to earn you points. But if you do a really good job, you could get some points.